Hello students, good evening. Welcome to another video of Vedantu Karnataka YouTube channel. This is Catherine, your physics master teacher. So, can you quickly let me know if I'm audible and visible? Check. Yes. Hi all of you. Welcome to the lesson. How are your preparations going? Okay. So I know all of you have your, FA1 or first unit test at different times. So, and some of you have different chapters as well. So we are trying our best to cover it as early as possible. So all of you can, utilize it for whenever you have the exam. So some of you have it in the first week of August, some of you have it in the last week of August. So we will be completing portions before that so that you can watch the video whenever you want. So what we're actually doing right now is we're doing each chapter and then 2 markers, 3 markers, 5 markers, 1 markers of that particular chapter. Okay, so after I take current electricity, I'll be doing questions on current electricity. Each of the teachers will be doing that. Is that clear to all of you? Hi RXBTCC, good morning. Sorry, good evening. Hi Harshit, good evening. Welcome to the class. So quickly, all of you go send the link to all your friends. Ask them to join. We're going to do current electricity in one shot. Okay. So in another 2 hours, I will teach you the whole of current electricity. Every important concept, I'll make sure it's crystal clear to every one of you. Okay. Are you all ready? If you're all ready, put some fire emojis in the chat. Quickly. I'm doing good. How are you doing? When is your FA1 or unit test? When is it? So let's start the lesson. Current electricity. Okay. So what do you all know about current electricity? So electricity is basically the flow of a charge. You might have learned that in school. So electricity is when if you have a wire, okay, something flows through the wire in your house and you'll say, okay, current flows through the wire. What is this current? What is flowing through this wire? So if you have a wire, okay, if you have a wire and electrons move through the wire or a charge moves through a wire. What is charge? Electron is a charge. So when this charge moves through the wire, what happens? Electricity flows through the wire. Yes? So electric current is what? It is the flow of charge through let's not say wire, it could be through anything that can conduct the electron. So generally we will say conductor. Okay? So electric current is the flow of charge. It is the flow of charge through a conductor. Why conductor? Because anything that can allow electrons to pass through is called a conductor. Okay? Let's look at that definition which we've written here. So electric charge is the flow of charge. Sorry, electric current is the flow of charge through a conductor. And what is electricity? Electricity is basically that energy that is produced when this flow of charge happens. Okay? So electric current flows because of energy. I mean, when electric current flows, there is an energy produced. That energy is electricity. Okay? Hi Rajeshwari, hi Sunita, welcome to the lesson. How are you all doing? Are you all doing great? Yes? Do you understand the difference between electricity and electric current? So electric current is the flow of a charge. Electricity is the energy that is produced when this charge flows. Yes? Are we good? Good to go? Okay? So now electric current, it can be represented by the alphabet I. Okay? Electric current is always represented by the alphabet I. And what is I equal to? I is equal to the amount of charge. What is current? I already taught you. Current is when charge moves through a conductor. So the amount of charge moving through the conductor in a particular amount of time is current. So mathematically you can represent current as charge divided by time. Okay. The amount of charge that is carried on a wire in a certain amount of time. Now let's say a small amount of charge is carried and let's say the small amount of charge is delta Q. And let's say the time interval is delta T. Now this can also be written as dQ by dt. Yes, because it's a small amount of charge, it can also be written as dq by dt. So now if you have a doubt on why dq by dt, you can go back to first few portion. I've already taught you how to take del and how to make it dq there. Okay, since this is a one shot, we don't have time to do that. Let's move on to the next topic. Is this clear? It's clear to Rajeshwari. Very good, Rajeshwari. Good, good. Okay, next is the SI unit of current. What is the SI unit of current? First, let's write down the formula for current. So, current has the formula charge by time. So, in some textbooks, it will be small letter t, q, small letter or capital letter does not matter. Okay. So, current is charge by time. So, what is the SI unit of charge? The SI unit of charge is coulombs. The SI unit of time is seconds. So, the SI unit of current will be coulomb per second. Or you can write it as coulomb second raised to -1. Okay. So, this is the SI unit of current. Now, this can also be called as, yes, very good, very good. It can also be called as ampere. Okay. So, this can also be called as ampere. So, ampere or ampere is also represented by the alphabet A. This is the SI unit of electric current. Okay. Very good, RXBTCC. In all my classes, my students watching this recorded will wonder who this is. No, I keep saying this name. It's one of my students. He gives me answers on the live chat. Okay. Yeah. So now what is 1 ampere? 1 ampere, it's represented by the alphabet A. 1 ampere can be written as 1 coulomb divided by 1 second. What does that mean? When 1 coulomb of charge passes through the wire in 1 second, it gives you current of 1 ampere. That is the meaning of 1 ampere. Okay? Perfect? Yes? Okay. Now let's look at the next topic, which is difference between conventional current and electronic current. So you know the SI unit of current, you know what is current. Now what is conventional current, what is electronic current? So many terms, right? Ma'am, electricity is so confusing, you might say that. Don't worry, I'm here to make it very simple for you. Okay? So first we will look at what is conventional current. So conventional current, what does the word conventional mean? Traditional. Okay? It's like a set of rule. It's like something that has been followed for so many years. So conventionally, current, is represented as to always flow from positive to negative. Okay? So conventionally, current always flows from positive to negative. And the flow is due to positive charge. The flow is due to positive charge. Okay? Do you understand that? So, conventionally, as I said, it's traditionally, which means this convention was made years back. Even before the structure of electrons and all were discovered, people believed that electricity or electric current always flowed from positive terminal to the negative terminal, and the flow was because of positive charge. This was something people believed. People continue to believe the same thing now. It's not because we don't know what the truth is, it's because it's a standard thing that is followed throughout the world. So we also follow the same thing. Okay. But after you study this chapter, you will realize why this is not correct. Now itself, I'll tell you that also. So conventionally, before so many years, scientists believed that current always flows from positive to negative. Okay. But if you look at the actual process that's happening, which is electronic current. Okay. So, but in reality, what happens? Current always flows from negative to positive. And what is current? Current is the flow of electrons. So obviously it is due to negative charge. Okay? It is due to negative charge. You understand that? So conventionally, people believe that current always flows from positive to negative. But in reality, current is the flow of negative charges. It is the flow of electrons. So it has to flow from negative to positive. Okay? Is this clear? So you can see when we do circuit diagrams and all that, you will see there, you'll always represent the direction of current. If this is your battery, okay, and this is the circuit, always direction of current you will represent from the positive terminal. That is because conventionally people use the same thing. Okay, so conventionally we use the notation the current always flows from the positive terminal to the negative, but electronically or in real life, in reality, actually it flows from negative to positive. So this is the difference between conventional current and electronic current. So you can see that, you can actually conclude from this that the direction in which electrons flow, okay, and current, they are opposite. What does that mean? So here current I've represented, but electrons, they actually flow in this direction. Okay, so current flows in this direction, electrons flow in the opposite direction. Okay, so the direction in which we represent current is not the actual direction. The actual direction of electron flow is the opposite. I hope this is clear to you. Can you quickly let me know in the chat if this is clear to you? Am I saying too much and confusing you? Yeah. Okay. So is this clear? Can I have some response? Okay. Next, what we are going to learn is the next important term in this chapter, which is EMF or electromotive force. Okay. So first we will look at these important concepts and then we will start doing all the important derivations. Alright. Why current is opposite to electron flow? Okay, RXBTCC. Okay, he has a doubt. So that is what I explained to you here. So that is just a conventional method that we use. Okay, so initially, see, now you know current is because of the flow of electrons. So you know current has to flow from negative to positive because it is because of the flow of electrons. That you know now because you know that current is because of the flow of electrons. But years back, people did not know that. Okay, so years back, if I have a bulb working and you don't know, okay, if you have something working, some electric appliance working, you don't know from which direction current is coming because you don't know it's because of the flow of electrons. So what happens? Scientists, all the scientists together, I don't remember who, but the scientists, they decided, let's take a conventional method and let's follow that universally. Okay, so they all decided we are going to make sure that every time we have a circuit, current flows from positive to negative. Later, scientists came and proved that it is from negative to positive, but still we follow the old convention itself. That's all. Okay? Is that clear? Is that clear? Yes. Rajeshwari, it's clear? Okay, very good, Rajeshwari. Wonderful, wonderful. Let's move on to the next term that we're going to learn, which is electromotive force, or it's also called as EMF. Okay, so you might have heard about this term, electromotive force, EMF, and all that. So what is that? It is basically the work done by some source, okay, to move one positive charge from a lower potential to higher potential. Okay, now what does that mean? Let's draw a circuit. Okay, imagine I have a battery and this battery is connected to a bulb. Okay, so this circle and cross is a symbol for bulb. Okay, it's connected to a bulb. So this is my circuit. Okay, so let's say I'll draw a smaller battery. This is too big. Okay. Okay, so the long one in a battery, always the long line is the positive terminal, the small line is the negative terminal. Okay, now what did we learn? According to conventional methods, current always flows from the positive terminal to the negative. So this is the direction of current. Okay, yes, so current goes this way, it goes this way, it comes back here. So this is the direction of current in this circuit. Okay, is this clear? Now, any charge from the positive, for it to reach all the way to the negative, it has to do some work, and that amount of work is divided by the amount of charge it carries. Yes, so the amount of work divided by the amount of charge actually gives you EMF, which is E. Okay, so EMF is the work done by a source, like a battery. Okay, so the work done by a source, in this example, it's a battery. It is a work done by a source to take what? To take one charge to one one charge from this terminal all the way to the other terminal. Okay, so what happens? The charge has to move. If this is a battery, the charge has to move from this terminal through the wire all the way till the other terminal. So that the amount of work done to do that is called EMF. Okay, so it's basically the total amount of work that the charge takes to drive it around the circuit, for it to run around in the circuit. It's like when you leave home, you carry all the food that you need to go to your, to go for your trip, and then you take everything that you need until you come back home. Just like that. EMF is like that. EMF is what makes the charge go through a whole circuit and then come back to the source. Okay? Is this clear? So what is EMF? What can you say it is? It is the work done by the source, okay, the battery, to move what? To move one positive charge from lower potential to higher potential. Okay, so from one terminal of the battery to the other terminal of the battery. All the work it does is called EMF. Okay, and mathematically you can say that it is work done by charge. It is EMF. And what will the SI unit be? What will the SI unit of EMF be? SI unit will be work done. Work done has the unit joules. Work done and energy will have the same unit. So it's joules divided by the energy for, the SI unit for Q is what? Coulombs. So this is basically joule coulomb raised to -1. Okay. Now there is one more unit, which is the famous unit. The unit is called volts or V. Okay. So EMF can be represented by volts or joule per coulomb. Okay. Is this clear to all of you? Yes. Now EMF can also be called as the maximum potential difference of a circuit. Okay. So what is potential difference? Potential difference also is a force that pulls a charge from one terminal all the way through the circuit to the other terminal. So the maximum potential energy can also be called as EMF. Okay. So that is also one definition of EMF that you can write. EMF is the maximum potential difference of a circuit. Okay. EMF is the maximum potential difference of a circuit. Is this clear to all of you? Still doubts? Yes, voltage and EMF. Yes, maximum, when a circuit has maximum voltage, it is equal to EMF. Okay. So the maximum potential or maximum voltage of a circuit is the same as EMF. But in between, if you have some components and that component uses up some voltage, then it will not be the same as EMF. But if you have an empty wire, you connect it across the battery, then what happens? The maximum potential difference and the EMF will be the same. Is that clear? Okay. Now let's move on to the most important law of this chapter. I'm sure all your PU teachers might have asked you to by heart this law. Yes, this is the very famous Ohm's law. Okay. What does Ohm's law state that? Ohm's law is a very simple law. It just means that if you have a conductor, okay, let's say you have a wire. Okay, any conductor, I usually take wires because that's something all of you know. Any conductor, anything that can allow electricity to pass through. Okay, you take a wire and you allow current to pass through it. Okay, so what is current? Charges. So these charges are passing through it. Okay, the amount of voltage and amount of current, they are going to be proportional. Now what is voltage? Voltage is the force by which these charges move. Electricity is the movement of charge. So how the charges move depends on how much force is applied to it. So voltage and current are always directly proportional for a conductor. Okay, but if I remove this proportionality, I can put an equal to and a constant. So this constant is called resistance. What is V? V stands for potential difference or voltage. I stands for current. Now, when I remove the proportionality, I put a constant. That constant is called as resistance. Okay. Now, what is resistance? I can mathematically say resistance is equal to V by I. But what is resistance? Resistance is basically just like the word resisting current. Okay, so if you have a wire which has a very high resistance, it means that it does not allow a lot of current to pass through. So it is like you have a crowded street. Okay, if you have a crowded street, a crowded street is like a high resistance path. It's very difficult for you to cross. Imagine you are current. It's very difficult for you to cross. Now, as the street gets less and less crowded, you can easily pass. That is the relationship between current and resistance. If there's a lot of resistance, you cannot pass. It's like a huge number of people. Okay? So obviously from this you should know that whenever resistance is high, current will be less. Whenever resistance is less, current will be high. Okay, so resistance is basically opposition to the flow of current. Okay, so what does Ohm's law states that? Ohm's law says that the current flowing through a conductor is directly proportional to the potential difference V. We already discussed this across its ends, provided the temperature and physical conditions of the conductor remains constant. So this happens at a single temperature. Okay, the temperature is a constant. Okay, so the value is not going to change. So if the whole thing happens at 10 degree, it should be at 10 degree only. If you increase the temperature, what happens? Particles in the wire will start moving faster. You have learned this in your younger classes. If you have a wire and you heat it, what happens? Particles will vibrate faster. So that means it's like a crowded street where people are running around. So it's impossible for you to cross. So what happens? Whenever temperature changes, the particles move faster, which will change the resistance. So if the resistance changes, then voltage and current will no longer be proportional. Voltage and current are proportional only at one single value, which is a constant value of resistance. Okay? So resistance R is independent of the value of V and I. Yes? It is just a constant. So V can be any value, I can be any value. Okay, but V is always proportional to I when resistance is constant. But if you say, even if the resistance is 10, 50, 20, it just has to be constant, that's all. Okay? Is Ohm's law clear to all of you? Hi, Shamila. Hello, anime fan. How are you? I'm good, I'm really good. Okay? It's good, no, when I see all of you coming in class and, inquiring and all that. How's the class, all of you? Let me know in the chats how the class is. Are you enjoying the lesson? Yes. So now we will, as I said, we will look at, I was talking about resistance. Now let's look at a deeper perspective of resistance. Okay. So resistance, I can give you another analogy or another relationship for resistance. Imagine you have a ball. Okay. You have a ball and it's rolling on the floor. After some time it stops. Why does it stop? It stops because of friction. Friction is stopping it. Now if there was no friction, the ball would just go, it would just roll forever. Isn't it? Friction stops it. Right? Resistance is just like that. So resistance is like friction. So resistance stops electricity like friction stops the ball. If resistance is very high, it will stop a lot of electricity. If resistance is very low, if resistance is very low, what will happen? It will allow a lot of current to pass through. Okay? Okay. Is that idea? Did you get the idea of resistance in your head? Okay, Rajeshwari is enjoying. Anime fan says the class is amazing as always. Hi Niranjan, welcome to the session. Is the concept of resistance clear to all of you students? Yeah? It's something that opposes the flow of current. And it is a property of a material. Okay, so imagine this is a wire. This is not a wire. Okay, I have a wire here. Yeah, imagine this is a wire. This is a charger, but let's say this is a wire that's, connected to something. So here, this wire has a particular value of resistance. And that resistance is because of the particles in the wire. If I take another wire, if I take this black wire, it have a different value of resistance. So each of these wires are made out of different materials. Each of these materials will have a certain value of resistance. So that is why we can say that resistance is a property of a material that opposes the flow of current. Okay? It opposes the flow of current through it. It only depends on the properties of the material. Okay? And resistance also tells us how much current will be there for a given voltage. Okay? Yes. So now, it resists the flow of current. It is a property of a substance. 2 points you know about resistance. We also know that resistance is equal to V by I. From the very famous Ohm's law, we know resistance is equal to V by I. So what will its SI unit be? SI unit will be, the SI unit of voltage is volts, SI unit of current is amps. So its unit will be V amps inverse, but its SI unit will be something called as ohm. I'm sure all of you have already, said the answer in your head, but yeah, ohms. Okay, so the SI unit of resistance is ohms, but there is one more unit of resistance which is volts per amps. Okay? Anime fan, no, nothing like that. Nothing is anime fan has asked if there is a material which has absolutely zero resistance. No, nothing in the world has, nothing is ideal. So nothing will have zero resistance. Everything will have some value of resistance. Okay? Yeah. Faraveen, how are you? I'm good. How are you? Welcome to the session. So did you all like the video? Please quickly go mark your attendance, go like the video. That is, that is a way where you show appreciation to your teachers. There's nothing else that we ask. Just like the video, subscribe to the channel, and go tell your friends that there is a channel that's even taking classes for FA1 and Unit Test 1. Can you imagine? Is there any other channel that's giving you this? No, we give you for whatever exam we had, took classes for exam 1, exam 2, exam 3, even for your supplementary, for everything we were here. Making last minute revision classes, 3 markers, 5 marks, anything. So please keep supporting our channel by telling all your friends that there is a channel. Okay? Because if we don't have your support, then we'll have to shut down the channel. We will not be able to move forward. So, okay? So I expect all of your support in our channel. Yeah. This is a channel made with so much love for all of you by wonderful teachers. Okay, coming back to the topic, resistance, the SI unit is ohms. Now, so what is 1 ohm? 1 ohm is basically 1 volt divided by 1 amps. Okay? 1 volt divided by 1 amps. Yes? Okay. Now, if you take a graph, okay, imagine I take a graph and I take voltage on the y-axis and current on the x-axis. Okay. I draw a graph with voltage on the x-axis and current on the y-axis. Now, if I draw 2 lines, these two have a different slope. So what would the slope of this graph be? The slope is basically change in y-axis divided by change in x-axis. What is V by R? V by I is R. So if you take the slope of graph A or graph B, you will get the resistance. Yes? Yes? You will get the resistance. Now imagine I draw a graph. I take the same graph, but I change the coordinates. So if I take I on the y-axis and V on the x-axis, what happens? I will get slope will be I by V. Oh my god, my V is pathetic. I by V, which is 1 by R. Okay, so depending on what graph you take, you can find out the slope. It will either be R or 1 by R. Now, depending on the value of slope, you will get the value of resistance. So, if there's a lot of slope, high resistance. Smaller slope, low resistance. Okay? Is the concept of resistance clear to all of you? The basic concept. Now what we learn is, we look at the factors that affect resistance. So we learned that resistance is the property of a material And we learned that resistance opposes the flow of current. Now, resistance should depend on something. It depends on the property, but what exactly does it depend on? That is what we're going to see under factors affecting resistance. Okay? So, first thing that we're going to learn, the first factor is going to be length. Okay? So, resistance is going to be proportional to the length of the conductor. Okay? Resistance is going to be proportional to length of the conductor. So, R proportional to L. Okay? So, what does that mean? That means more the length, more the resistance. But that's actually, you can actually think of it that way, right? So, imagine you have a wire. It's this long. Let's say it has certain value of resistance. So, current is opposed. If I take a longer wire, won't current be opposed for a longer time? So, wouldn't resistance be more? Okay? So, longer the conductor, more the opposition to resistance, longer the conductor, more the opposition to current. So, more opposition to current means what? More resistance. So, wouldn't R and L be proportional? Yes? So, when R increases, shouldn't L also be increasing? Basic. You can just think. I think if you think with your common sense, you'll get it, right? If it's a small wire, it'll have a small amount of resistance. Next factor affecting resistance is area or area of cross section. Okay? Area of cross section. Now you tell me, how would it affect? Imagine you have a wire that is, let me draw this. Okay, so this is the cross section of the wire. Okay, this part is what I have drawn. So imagine there's two wires. One is this size and the other is this size. Okay, these are two wires. Okay, through which one would current be able to flow easily? Tell me. Yes, obviously the bigger area one, because current can easily flow through this. So this is more narrow, so it will be difficult for current to flow through this. So how should current and resistance resistance and area be related? So when there is a lot of area, current can easily flow through, so resistance will be less. Okay, so when there's small area, current cannot pass through, so resistance will be more. Okay, I can draw that. I can do a better job with drawing that. Let me try. So let's say this is my first wire. This is the area A. This is my second wire. And this is its area A. Okay. So resistance will be proportional to 1 by area. More the area, less the resistance. So here current will be more, resistance will be less. Okay? Yes? Okay? Okay, ma'am, in school we did Ohm's law experiment and I got graph perfectly. Super. Very good. Yeah? So that is because you did that experiment at a constant temperature and a fixed resistance. So you will get Ohm's law graph perfectly. Okay? Very good, very good. Area, temperature, length, nature of material. Very good, Praveen. Pratham. So if you get a lecture like this, now you should go tell your juniors. Okay, please make sure you send this video or send the channel link to all your juniors. Let them also learn. Okay. Hi Rakshita. Hi Sanant. Hi Rajeshwari. Okay, Rajeshwari gave me the answer. Big one inversely. Very good. Very good. Very good. Superb students. You're all doing really well. You're always doing well, no? So we've looked at length, area of cross section. So we have R is proportional to 1 by A. Now let's write these together. So now what all do we have? Let's take a different color. How is violet? Violet is a good color, no? Yeah. So let's say R is proportional to L. It's also proportional to A. So now R is proportional to L by A. Now every time I remove the proportionality, I have to put an equal to symbol and a constant. So here also I do the same thing and I add a constant. This constant is called resistivity. Okay? resistivity. Yes. So this constant is called as resistivity. And what does resistivity depend on? Oh my god, so much of dependence, no? Yeah, they're all dependent. So resistance depends on length, area and resistivity. This resistivity now depends on the nature of the material and the temperature. Okay. So what all does this resistivity depend on? Resistivity depends on, can you see or are you seeing my head where I'm writing? I think you can see. Okay, resistivity depends on nature of material and temperature of the material. Okay. So these are the factors affecting resistance. Length, area of cross section and resistivity. This resistivity is a property of a material that depends on the nature of the material and temperature. Okay. So factors affecting resistance, is it clear? Clear? Pratham followed my content. Good. Okay. It's good. Okay. He said it's good, not me. Okay. Thank you, Pratham. Please make sure you give this channel details. Okay. Tell all your juniors because, students might not know. So let nobody miss out on, good content because we have lots of good teachers here. All your biology teachers, the other physics teachers, chemistry, every teacher is doing a really good job, I believe. So please make sure people get to know about this. Okay. So please do subscribe. Make all your friends subscribe. Now during this class itself, all of you quickly send this link. Tell all your friends subscribe and come and tell me in the chat how many of your friends subscribe. Okay? Yeah. Harshini, hi. Okay. Factors affecting resistance is clear. Let's move on to the next topic. The SI unit of resistivity. So now we learned a new term, resistivity. What does resistivity depend on? Nature of material and yes, temperature. So resistivity, how will I find the unit? Let me write down the formula first. This is the formula. So rho is what? Rho is RA by L, simple cross multiplication. So now let's write down the units. The unit for resistance is ohm. The unit for area is meter square. The unit for length is meters. So this becomes ohm meter. Okay. So this is the SI unit of resistivity. The SI unit of resistivity is ohm meter. Okay. Cool. Yes. Okay. Now we can classify, as I said, resistivity is something that depends on, the nature of a material. So you can obviously classify resistivity based on the different kinds of materials. So for conductors, it will have a different resistivity. Insulators will have a different resistivity. Semiconductors will also have a different resistivity. Okay. So what will the resistivity of conductors be? For conductors, what are conductors? Conductors are materials that allow electrons to pass through very easily. So they should have a very small amount of resistivity because they will have a very small amount of resistance because electrons are easily flowing through. So resistance is very small, resistivity also very small, and they have a range of 10 raised to minus 8 to 10 raised to minus 4 ohm meter. Okay, so it's good if you can know these values. Now, a semiconductor is something between a conductor and an insulator. So they don't conduct as good as a conductor nor as bad as an insulator. So they will have a value from 10 raised to minus 4 to 10 raised to minus 6. Now for an insulator, it will have a value of, it will have a very high value because insulator is what, like plastic, this pen. This pen will not conduct anything. This is plastic. Okay, I don't know what's inside, but yeah. But this won't conduct anything. So it will have a very high value of resistance, a very high value of resistivity. So the value will approximately be greater than 10 raised to 8 ohm meters. Okay. So this is the relationship between this is the different values, the range of values for resistivity of a conductor, semiconductor and an insulator. Yes. Good, Rajeshwari. Rajeshwari had given me the unit ohm meters. Very good. Superb. Okay. Is this clear to all of you? So I have put that in a table as well. The values if you want to look at them. And there are examples also. You can quickly look at them. Conductors, semiconductors, and insulators. Okay, next, let us look at the temperature dependence of resistivity. Okay? Yeah. Are you all following? I hope you all are. Okay. Temperature dependence of resistivity is what we are going to look at here. So as I said, what is resistivity? Resistivity is something that depends on two quantities, what do I say? Two things. Okay. The nature of the material and the temperature. So for nature, we know how it depends for conductors, insulators, and semiconductors. Now let's see how it depends on temperature. So this I already discussed. What happens when temperature increases? The atoms in the metal, they vibrate more vigorously. They vibrate, no, they vibrate a lot. Okay. So when they vibrate a lot, what happens? They hit against each other more. See, imagine I take a closed classroom. Okay. No teacher. Full freedom. Okay. I take a classroom and I put 20 people inside. Okay. So the moment the teacher goes out, these 20 people will start running around. So if they start, imagine they're all blind, okay? What happens? They will go hit against each other. So they will all go collide against each other. So what happens? Imagine even if the teacher comes in, it will be very difficult for her to go in because these students are running around. Okay, I'm just giving you a hypothetical condition. Okay, I mean hypothetical scenario. I know it sounds stupid, but sometimes stupid examples are things that you remember. Or I used to be a student like that. If I think about imaginary stuff, I used to remember. Okay, so you might be thinking, oh my god, why am I like this? Okay, jokes apart. So whenever temperature increases, the metal atoms, they vibrate very fast. They vibrate very fast. They hit against each other more and more. So what happens? It is very difficult for an external electron to pass through. Because here, there's lots of things happening. They're all hitting against each other. They're all running around, all the particles. So the external electron cannot pass through. So what happens? If electron cannot pass through, what is the passing of electron called? It's called current electricity. So there is no current. If there's no current, there is high resistance. So if there is high resistance, there is high resistivity. So as a result, when temperature increases, resistivity increases. Okay? Yes. Yes, yes. Now, shall we derive the relationship? This derivation is important. Shall we derive the relationship between temperature and resistivity? So, to derive the relationship, first let us say that the change in resistance is proportional to how much the temperature changes. Okay? So, how much resistance changes? It depends on how much the temperature changes. Now, how much the resistance changes is also proportional to the initial value of resistance. Okay? Yes. So initially, if the resistance had a value, the amount of change depends on that initial value. It depends on how much temperature changed as well. Okay? Now together, so we can say delta R is proportional to what all? Delta T and R1. Can I say that? Can I say delta R is proportional to delta T and R1? Yes. Yes. Okay. Now what I will do, I will remove the proportionality and I will put an equal to. So I will put an equal to. So this becomes delta R is equal to. Now I'll put a constant. Now this is not proportionality that I'm going to write. This is my constant. This constant is called alpha. I know it looks just like the proportionality, but no. Okay. So this is alpha delta T R1. Okay. So please, all of you should follow. What I've done is I've removed proportionality and I've put equal to an alpha. Okay. Are we good till now? Now what is the next step? Now next step is I will write delta R as what? Delta R is what? The difference in resistance. So delta R can be written as R2 minus R1. This is equal to alpha. Delta can be written as T2 minus T1 into R1. Okay? Can I do this? Yes? I think I can write it here itself. Let's not break the flow. So delta R, I'll write it as R2 minus R1 is equal to alpha T2 minus T1 into R1. Okay? Now, I'll take R1 outside. No, not R1 outside. So what do? I'll take R1 to the other side. So I will write R2 is equal to alpha T2 minus T1 R1 plus R1. This R1 is from the other side. Okay, plus R1. Now I can take R1 outside. So what will this become? If I take R1 outside, what remains? There's 1 plus alpha T2 minus T1. Can I do that? Can I do that? Okay. So some of you might be wondering why I put this R1 here. Okay, basic math. But some people get confused with all this. So I will just put R1 here, R1 plus. Okay. So now I have R2 is equal to R1, 1 plus alpha, T2 minus T1. Now what is R? Resistance. What is the formula for resistance? We have already learned the formula for resistance. So R is equal to rho L by A. Yes? All of you, R is equal to rho L by A. So R2 will be what? Rho 2 L by A is equal to R1 is what? Rho 1 L by A into 1 plus alpha T2 minus T1. Okay, L and A, they are going to be the same thing. It's not going to change. Same wire, right? So L and A will cancel. So what remains? Rho 2 is equal to rho 1, 1 plus alpha T2 minus T1. This is the formula for resistivity. Okay, so this is the relationship between temperature and resistivity. Let's put a box. Boxes look nice, no? I like boxes. So let's put a box. Where is box? Shape box. Okay? Is this cool? Yes, Niranjan. Why are you calling me? What happened? Niranjan's calling me ma'am. Yes, Niranjan. Ma'am, I can hear you. I can see you. You can tell me. Is this clear to all of you? Any doubts here? So what did we start with? We started by taking resistance is proportional to change in temperature. It's also proportional to initial resistance. Okay. So alpha 2 is equal to alpha 1 times 1 plus alpha. Sorry. Rho 2 equals rho 1, 1 plus alpha T2 minus T1. Okay. Any doubts still here? If there's no doubt till here, can you put some fire emojis in the chat? Quickly. Fire emojis in the chat. That's what's keeping our class live. Okay? This much is clear. Let's move on to the next topic, which is current density. Okay? Current density. What is current density? Imagine you have a conductor. Okay? A conducting wire you have. Let's say this is the area of the conducting wire. Okay? So this is the area. Now, if the current passing through it is I, okay? Current density is equal to the amount of current passing through a certain area of wire. Yes. So what is current density? The amount of current passing through a certain area. Now I will put a symbol for current density. I will call it J. Okay, nice alphabet, no? So now what? J is what? Current density. Current I already know it's I. Area I know it's A. So J is equal to I by A. I have a new formula. J is equal to I by A. Okay. Now let's let's write down this formula in terms of I and A. Now, what is I? J can also be written as, what is I? Charge by time. A is A. So, J can also be written as Q by T into A. So, these definitions, multiple formulas and all you need when you do questions. So, imagine you get a question and they ask you find current density, and they don't give you current, but they give you charge and time. You should know that current is charged by time. I'm sure all of you will know because you are following Vedantu Karnataka lectures, no? Yeah. Okay. Hi Akshay. What are you doing? Everybody's busy listening to the class, Akshay. Hi Bharati. Welcome to the lesson. Okay. Niranjan and Rajeshwari has understood. Okay, very good students. Alright. Now, so what is the definition of current density? It is the amount of electric current flowing per unit cross-sectional area of a conductor. Or in simple words, you can say it is how much current flows in an area. Okay? How much current flows through a given area. Easy? Yes? Okay? Are you all happy with this part? Current density is very easy. Current density and all, very easy. But here one thing is, area and current are perpendicular. You can see here. So if this is the area, current is flowing like this. They're perpendicular. But what happens if the current is passing straight, but the area is like at an angle? Okay. Okay. So right now area and current are perpendicular. But what happens if this is current, okay, and area is like this? So the wire is like this. Okay. So the wire is like this and current is passing through like this. So in such cases, what will you do? As always, you've learned what you do in vectors. No, you resolve it into two components because, if it's like slanting to an angle and all, we don't know what to do. So what you take a horizontal component and a vertical component. Okay. So area is along this direction. This is area along that direction. So always horizontal component is what? A cos theta. Vertical component is always A sin theta. But anyways, vertical we'll just ignore. Why? Current is flowing along A cos theta only. So you don't have to consider A sin theta. So now what will current density be? Again, current by area. But this time the area will be A cos theta. That's all. So from this I can write current is equal to JA cos theta. So current is equal to J dot A. Yes, very easy. So this is the current density when area is at an angle. But if area and current, they're along the same plane. Okay, not perpendicular, they're along the same plane. Okay. So if this is the area, current is along the same plane, then you can say that J is equal to I by A. So this is when this is the formula for current density when current passes at certain angle. Is this clear to all of you? Yes. Hi Naveen, how are you? Welcome to the lesson. Okay. Akshay is from Udupi. Tell all your friends in Udupi to watch the channel, okay? Send the link to your class groups. Okay. Is that clear? That much is clear? So let's move on to the next topic, which is conductance and conductivity. This is also super easy, students, very easy. What is conductance? Conductance is basically 1 by resistance. That's all. Okay? Conductance is 1 by resistance. So what should its SI unit be? The unit of resistance is ohm. So the SI unit should be ohm inverse or 1 by ohm. Okay? Now what is conductivity? Conductivity is 1 by resistivity. Okay. So conductance is 1 by resistance. Conductivity is 1 by resistivity. Okay. So 1 by resistivity. So what will its unit be? Do you remember the unit of resistivity? It was ohm meter. So 1 by resistivity is ohm inverse meter inverse. Very easy. Conductance, conductivity done. Yes. Any doubts till your students? Thank you, Akshay. Okay, tell all your friends to watch Vedantu Karnataka YouTube channel. Okay. Hello, Pushkar. Hello. Welcome to the lesson, Pushkar. Are you all enjoying the session till now? How's this one shot for electricity? Is it going well? Yes? If it's going well, put some fire emojis in the chat. So this is conductance and conductivity. Okay? Yes. Let's move on to the next topic. Next, from here, the very important derivations start. Okay, obviously the previous derivation where we did relationship between time and resistivity is also important. But from here you will get for sure derivations. Okay, so drift velocity and all we are going to start learning from here. Yes. So first we will start with the mechanism of current flow in a conductor. What does that mean? That means how current flows in a conductor. Okay, we are going to see how current flows in a conductor. So right now you know current flows because electrons flow in the conductor. That's how current flow. But right now we are going to see how that happens. Okay, so in this, when we learn this, we will learn two new terms. What are the terms? Drift velocity and relaxation time. Okay, so those are the two new topics that we are going to learn how when we learn the mechanism of current flow in a conductor. Okay, okay, let's look at drift velocity and relaxation time. Okay, yeah. So what is drift velocity? Drift velocity is the average velocity acquired by free electrons in a conductor under the influence of an external field. Oh my god, what is this? Yeah. So it's basically, imagine you have, okay, let me draw this. So, okay, this is the definition of drift velocity and relaxation time. So, relaxation time is basically the average time between two successive collisions of a free electron. So, what is drift velocity? Drift velocity is the velocity by which electrons move. Okay. And what is relaxation time? Imagine there are two electrons and they're moving. There are so many electrons. Okay. So, these two, this is moving and they hit. The time taken until they hit again is called relaxation time. It's basically the time they relax. They're relaxing and going until they go and hit something else. Okay, so that time interval is relaxation time. Okay. Yes, good evening, Swati. Welcome to the lesson. Okay, so now we will look at them in detail. Now, imagine there is no battery connected. Okay, so this is a wire in the absence of a potential difference. So there is no battery. This is a simple wire. Okay. So what happens? Particles are all randomly moving. Particles are all randomly moving. Okay. So since they're all randomly moving, the total drift velocity will be 0. How is the total drift velocity going to be 0? That's because they all move in random directions. Velocity is a vector quantity, so they all cancel out. Okay. Yes. Now, in the presence of a potential difference. Okay. So when there is a potential difference, what happens? That means what? You are connecting a battery. Okay, let's put a key also. So in the presence of a potential difference means you are connecting a battery. So because of the presence of an external electric field, okay, because of the presence of an electric field, all the particles align in one direction like this. Okay, all the particles align in one direction. So obviously they together will have a velocity. So drift velocity will not be equal to 0. Okay. Yes. Swati, velocity is 0 when there is no potential difference. So if I simply have a wire or a conductor, it will not have any drift velocity. But if I take a wire or a conductor, connect it to a battery, and I give an external electric field to it, then what happens? All the electrons will align in the direction opposite to the direction of the electric field, and it will together have a velocity. So drift velocity will not be equal to 0 because yes, as you said, Swati, electrons will flow in one direction. Okay, very good, Swati. Yes, AJ, hello, welcome to the class, AJ. Is this clear to all of you? Okay, now let's do the maths behind this. What physics without derivations? Yeah, okay. So now let's say V is equal to U plus AT. Okay, this is the equation of motion kinematics. Last year, all of you learned. Now, initially, what happens? There is no movement. So, initially it is 0. So, V is equal to, V is drift velocity. Initial velocity is 0. 0 plus A is acceleration. Now, the time taken between the time interval, I will take it as relaxation time and it's going to be represented by tau. What is relaxation time? The time interval between two collisions. Okay. So, Vd is equal to A tau. Okay. So from this I will get Vd is equal to A tau. This is my first formula. So this is the basic formula for drift velocity is acceleration into relaxation time. Okay. Now what will we do? Now let's assume also F is equal to ma. We know from Newton's second law F is equal to ma. Okay. So from the first chapter, electrostatics, we also know when there is a charge and there is an electric field, the force is QE, charge into electric field. And QE is equal to ma. Okay. So E is equal to, E can be written as, wait, I will erase this. Which color? Violet, no? Yeah. So what is the charge here? So here electrons are moving. So instead of Q, can't I write it as minus E? So the charge of the electron is minus E. So Q is general form for charge. So I will just put it as minus E into ma. So from here I will get acceleration is equal to minus E by m. This is my second formula. Okay. Now from this I can write, putting 2 in 1, I can write Vd is equal to, instead of acceleration I will write minus E by m into tau. This is the formula for drift velocity. Okay. Is this clear to all of you? Yes? Clear, clear, clear? Hi Dinesh, namaste. Yes, Akshay, no views, what to do? No, people are not interested nowadays. Only before exam they will. Okay. So Akshay has to help me support the channel. Okay. Yeah. Please send this to all your juniors, seniors, friends, everybody. Is this formula clear? Okay, Swati says yes. Very good. So Vd is equal to minus em by tau is the basic formula for drift velocity. So from this, what does the minus sign represent? Why minus? So if electric field is along this direction, then actually electrons inside the wire move in the opposite direction. Okay. Electrons inside the wire move in the opposite direction. That's the meaning of the minus sign. So as I said earlier, those who came late, you missed on that very important part. I gave them a very important part in the beginning. Okay. Yes. So in this figure, you can see electric field is from positive. Okay. Electric field is along positive, but electrons are in the opposite direction. So that is what is represented by the negative line. Okay. Yes. Negative sign represents that. Is this clear? Clear, clear? I will give you good lectures, Akshay. I will give you good physics lectures. Okay? Yeah? That's the only thing I can give you. So all of you who are there in the chat, quickly go ask 5 friends to subscribe and quickly come back and tell me how many friends subscribed. Okay? Yeah. Okay. Is this clear to all of you? Next. What is the next part? Next is relationship between drift velocity and current. Okay, we saw first, what did we see? The relationship between, the formula for drift velocity. Now the relationship between drift velocity and current. Let's do that. Are you all ready to do that? Hi, it's Niru. Okay, let's do it. Relationship between drift velocity and current. Again, you have a conductor. Okay, the conductor has an area A. The length of the conductor is L. Okay, okay, is this clear? Okay, now I will write it on this side. Let N, okay, what is N? N is equal to the number of electrons. Number of electrons. N is the number of electrons divided by the volume of the wire, which is basically the number of electrons by volume is basically what? Electron density. Okay, this is the electron density. So N is the electron density. Now we know that what is current? What is current? Current is obviously charge divided by time. Now what is charge? How much charge passes through the wire? It depends on the number of electrons passing through the wire into the charge of one electron. Do you all agree to that? Okay, so the total amount of charge passing through the wire is the number of electrons into the charge of one electron. Okay, so from this now what all can I write? I can write I is equal to number of electrons into the charge of one electron. I can write that as N into V. Okay, number of electrons I will write it as N into V into the charge of one electron. How did I write number of electrons as N into V? First formula, N is equal to number of electrons by volume. I just rearranged it. Simple math, Yeah, divided by time. Now what is volume? Volume is nothing else but area into length. Volume is side into side into side, which is area into length, into the charge divided by T. Yes, Tt. Now what do we have? We have current is equal to minus E N A. I'll put L by T like this. What is L by T? Distance by time is what, students? Yeah, distance by time is speed. So L by T I will write it as Vd. So now I have the formula relating drift velocity and current. What is the formula? I is equal to minus E N A V D. Superb. Yes. Yes. Is this clear to all of you? This is the relationship between drift velocity and current. Are we good? Are we good here? Yes. Oh my God, people are asking other people's gender. What is happening in the chat? Somebody's birthday. Oh, it's Niru's friends are commerce. Why don't you have any friends in science? Hi, Monster Gang. Welcome to the class. I am good. How are you, Monster Gang? Okay, let's move on. This is clear, all of you. I believe this is clear, all of you. Next, the very famous derivation of Ohm's law. Okay? I is equal to so from this you can also say that current is proportional to drift velocity because minus E is the charge of one electron, N is a constant, area is a constant. So taking all of that as a constant, you can say I is proportional to Vd. Okay, so that also you should mention. For relation between drift velocity and current, you should mention that I is proportional to Vd. Okay. Yes. Okay, now the very famous, the very important deduction of Ohm's law. This is very important, students. Very, very important. Okay, deduction of Ohm's law. Okay, So now what are the formulas that we know? The formulas that we know are I is equal to minus E N A V D. This is a formula that we know. So from this I can write, I also know that VD is equal to minus E tau by M. These are two formulas that I know. Okay. Yeah. Students, what are you all doing in the chat? All of you listen to my class. Yes. Okay. Swati is putting okay. Very good. Okay. So I is equal to minus N E N A V D. VD is equal to minus E tau by M. Very good. Now what will I do? I will take I to be equal to minus ENA as it is. Instead of VD, can't I write minus EE tau by M? Yeah. So now let's multiply. E into E is E square. Okay. So the minus minus will become plus E square N E A tau by M. So E square N E A tau by M is your current. Now let's write that here. I take it, make it a little more thick. Okay. So now current is what? Current is E square N A tau by M. Tau by M. E square N A tau by M. E. Instead of E, I will write it as V by L. Okay. How did I get that? In my last chapter, electrostatics, I've taught you that electric field dE is equal to the negative potential gradient of dV by R. Remember? So E is equal to V by R. So similarly, here V is voltage, L is length. So this V is not volume. Okay. This V is voltage divided by length. Okay. Now, when I rearrange this, what will I get? When I rearrange this, I will take V to the other side, okay? So, I want to find the equation in terms of V. So, V will be equal to M L I, the whole divided by E square N A into tau, okay? So, I'll just take I outside. I'll take I outside. So, I get this much as a constant, okay? I get this as a constant. So now we already know, what do we know? We already know V is equal to R into I, Ohm's law, and V is proportional to I. So shouldn't this quantity be R? Yes. Shouldn't this quantity be equal to R? Yeah. So we can say that at constant temperature and dimensions. At constant temperature and dimensions, ml divided by E square Na tau is a constant. And this constant is equal to resistance. Okay? This constant is equal to resistance. And this resistance is the same as rho L by A. Resistance is the same as rho L by A. So, I can say rho is what? Rho is what? R A by L. So, which is basically M by E square N tau. Okay? Yes. So, this is the deduction of Ohm's law. Is this clear to all of you? Quickly let me know in the chat, students. So what did I do? I first took the formula of I and the formula of VD that we already derived. Okay, both these formulas, and then I put VD inside I, and then V by electric field I wrote it as V by L. So electric field is potential by length. That is from electrostatics. Okay, and then I take potential to one side and I solve the rest. Okay, so this is how you deduce Ohm's law. Any doubts here, students? Any doubts? Anybody? Any doubts? Anybody? Yes? No? Okay. I hope it's clear to all of you. Okay. So this is deduction of Ohm's law. Ma'am, important definitions, ma'am, please. Sumit Kumar. This is one short video. Everything I do today is important. Okay. And whatever definitions you need, I have put that definition in words. Okay. Yeah. Next is mobility of charge carriers. So mobility is what? Mobility is basically the drift velocity, how it can move. How does it move? It moves with our drift velocities. How does a charge move in an electric field? It moves with drift velocity. And mobility is what? The drift velocity acquired by a charge carrier in a unit, per electric field. Okay. It is, so you can also say it is how easily charges can move in a field. Mobility is how easily something can move. Okay. So if I can walk easily, I am mobile. I can move. I have good mobility. So mobility is how easily something can move. Yeah. Okay. So mobility of a charge carrier is how easily a charge carrier can move, and it is represented by the alphabet mu. Okay. Sumit Kumar, today I am doing only important things. This is your FA1 perspective. Important things, definition and derivation. That's all I am doing. No extra content. Okay. So in everything of this video is very important. Okay. So this mobility is basically the drift velocity of charge per unit electric field applied. So you can write mobility is equal to drift velocity, the whole divided by the electric field. So how much drift velocity is applied in a particular electric field. Now what is the value? Mu is equal to Vd by E. Now what will its SI unit be? SI unit will be, velocity is what? Meter second raised to minus 1. Electric field is Newton Coulomb raised to minus 1. So this together will become, mu will have the unit meter second raised to minus 1, Coulomb Newton raised to minus 1. Okay? Yes? This is the SI unit of mobility. Is it clear? Yes, yes. Tell me. Okay. Next, what we're going to do, we're going to define a relationship. Okay? Relationship between mobility and electric current. So these are all very important derivations, students, but very easy derivations. So we know that electric current is what? Minus E N A V D. This we already learned, already derived. Now we also know that mobility of an electron is what? Drift velocity by electric field. Now what we should do? Simple substitution. So from this we get drift velocity is what? Mobility into electric field. So simply substitute drift velocity. So current will be minus ENA. Instead of drift velocity, I will write mobility into electric field. So I is equal to minus ENA mu E. I can write this as a constant term, and then, sorry, mu is not constant. Mu is how the charges move. So minus ENA and electric field, all these can be written as constants into mu E. So I will get my electric field is proportional to mobility. Okay. So if this is equation 1 and this is equation 2, how did I get this? Putting 2 in 1. Okay. Yes, is this clear to all of you? So this is the relationship between mobility and electric current of a conductor. Okay? Yes. Are we good to go? Okay. Next, we will look at some limitations of Ohm's law, and then we will look at a small part of superconductors. Okay. Limitations of Ohm's law. So Ohm's law is mainly for ohmic conductors. What are ohmic conductors? Conductors that obey Ohm's law. Okay. So for any conductor that obeys Ohm's law, it's called an ohmic conductor. Okay. And usually metals. So for any ohmic conductor, if you take a graph of current versus voltage, it will be a straight line, which means current and voltage are always going to be directly proportional. Okay. It's going to be directly proportional. Now for non-ohmic conductors are conductors that do not obey Ohm's law. So what happens? For those conductors, if I draw a graph of I versus V, what I'll get is I'll get a curve like this. Okay, it won't be proportional. It can take different shapes, but it won't be proportional. An example for a non-ohmic conductor is a semiconductor, which you will learn. There is a chapter dedicated to semiconductors. Okay, so right now what you need to know is Ohm's law is applicable only for ohmic conductors, and for Ohm's law, IV graph should always be a straight line. Resistance should be a constant, and examples are copper, aluminum, and all. Non-ohmic conductor is not that important now. Okay? Yes. Is that clear? Yes? Okay. Vijay, ma'am, what time is first PU class? Students, first PU class, okay, Vijay as well as others, first PU class is taken by 3 physics teachers right now. So chapter 1 and chapter 2, it's already there in the channel. Okay, Sambhavi ma'am and Supreet sir have already done the lessons. You can go check Vedantu Karnataka YouTube channel. So those 2 lessons are already there. Okay, so chapter 1 and chapter 2, I have also done videos, but those won't be under FA1. You can check my videos as well. You can check their videos as well. Chapter 3, I will be doing Monday or Tuesday. Okay. Chapter 1 and 2 I have already done in the channel. You can check the videos. Does that answer your doubt, Vijay? Okay. Now we'll learn a small gist of superconductivity. Not that important, but yeah. So what is superconductivity? It's when the resistivity of certain materials drop to 0 when they are cooled. Okay, so you take some materials, you cool it to very low temperature. A temperature very low such that it's below critical temperature. Okay, if you cool it to very low temperature, its resistivity becomes 0. Okay, so that is superconductivity. Superconductivity is you take some material, certain materials. Okay, you can't take all, you take a certain type of material, you cool it below a very low temperature, the resistivity becomes 0. That's all. That's all that you need to know about superconductivity. Okay. Vijay, I take classes at 8 p.m. Okay. So whenever I take my class, it's usually at 8 p.m. I don't take it other timings. Okay, Vijay? So please inform your other friends also to join the classes. So things you need to know under superconductivity is that it is cooled below critical temperature and it offers 0 resistance. When it is cooled, resistance drops. Okay. Now it also produces an effect which is called the Meissner effect. So Meissner effect also not that important to you, but let's just learn it. Okay. So imagine these two are the two materials. Initially what happens? Initially if there are magnetic field lines, they just do this, pass through the material. Okay, so this is when the material is at a temperature which is greater than the critical temperature. But if the temperature reduces to a very low temperature such that it is very less than the critical temperature, what happens? Now these field lines, they cannot pass through the material. See, they pass like this. So this effect is called Meissner effect, and this effect is actually used in trains and all that. So if you're curious about this, after class you can go to YouTube and check for superconductivity and levitating trains. Okay, so you will see trains that are just floating. So they're floating because they have they are superconductors. So they have a magnetic field, and the magnetic field is not passing through them. It passes like this. So it lifts the object. Actually, superconductivity is really cool. You can go check YouTube videos on superconductivity. You'll be fascinated. It's a very cool phenomena. Okay. So what happens is it behaves, it does not allow magnetic field lines to pass through it. That's all. Okay. So that effect is called Meissner effect. Now those who want to look at the definition can also look. I put it here. It is the expulsion of magnetic field lines from the interior of a material when it is cooled below critical temperature. So magnetic field lines are expelled. They are not allowed to pass through the material. Magnetic field lines initially could pass through, but after it's cooled down, it's not allowing it to pass through. So that is called a superconductor. And this effect is called Meissner effect. Okay, that's all that you need to know about superconductivity. Now let's move on to a very important topic, which is resistance. Resistance in series and parallel. It's very important but very easy. Okay, resistance in series and parallel, very important, very easy topic. Let's quickly do it. So what does resistance in series mean? It means that one resistance. Oh, what was that? My resistor got converted into an arrow. There's one resistance connected to another resistance, connected to another resistance, connected to another, and it just goes on like that. So these are resistances in series. Okay. So let the first one be R1, second one be R2, third one be R3. Okay. R1, R2, R3, and they all have the same current. This is the most important thing that you need to know. Okay. They have different voltages V1, V2, V3. Okay. If you know this much, then you can easily do the derivation. So whenever something is connected in series, they will have the same current but different voltage. The total voltage coming from the battery will be split up between all the components. But all the components will get the same current. Okay. Students, that is something that you need to know. A series circuit always has fixed value of current, different values of voltage depending on the components. Okay. So the total voltage of a series circuit will be V1 plus V2 plus V3. Okay. What is V according to Ohm's law? It's IR. So here it will be IR1 plus IR2 plus IR3. Why I am putting I? Because it's the same. I is constant throughout. So I and I can actually cancel. So IR is equal to I into R1 plus R2 plus R3. So I and I cancel. So R will be R1 plus R2 plus R3. So total resistance in series is basically the sum of individual resistances. Okay. Now imagine I have a question. You have three resistances. Okay, two resistances. Find out R. This is 2 ohms, this is 5 ohm. So R will be 5 plus 2, which is 7 ohms. Is this clear to all of you? Yes? Clear? So to do this, one important thing you need to know, in a series circuit, current is the same, voltage is different. This is the opposite in parallel. So now you tell me, in a parallel circuit, what is same? Voltage should be the same, no? In a series circuit, if current is same, in a parallel circuit, what should be same? In a parallel circuit, then current should be different, voltage should be same. So let's draw a parallel circuit. Parallel circuit is when all the components are connected across one single point. So you can see they're all connected across that point. So this is R1, this is R2, this is R3. They're all connected across this point and this point. Okay. So if you have a current I coming in, let me use a different color. Okay. So if you have a current I coming in, so I on this arm will be I1. Here it will be I2. Here it will be I3. Okay. But voltage is going to be the same everywhere. V, V, V. Okay. So in a parallel circuit, voltage is the same. In a series circuit, current is the same. Okay. So now here what will current be? It will be I1 plus I2 plus I3. Remember in series, what did we do? We did V is equal to V1 plus V2 plus V3 because voltage was changing, isn't it? But in parallel, current is changing. Now what is current? V by R. So this is V by R1 plus V by R2 plus V by R3. Now all the V's are, I can take it outside. So this is V by R is equal to V into 1 by R1 plus 1 by R2 plus 1 by R3. So V and V cancel. So what remains? You will get 1 by R is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Okay. So this is the formula for total resistance in parallel. Okay. Is this clear to all of you? Parallel is clear? Okay. Now let's look at the next topic, which is heating effect of current. So one thing that you should know is whenever current passes through a wire, okay? So whenever current passes through a wire, it heats up the wire. Alright? So that's the first point that you need to know here. So when electric current flows through a conductor, some electrical energy is converted into heat energy. And this phenomena is known as heating effect of current. Okay? So what is heating effect? Whenever current flows through a current carrying wire, it heats up. Okay? And that heating effect is called as heating effect. And that process is called as heating effect of a conductor. Okay? Now, heat produces by electric current, and that's also called as Joule's law of heating. Okay, so heating effect of a conductor is also called as Joule's law of heating. Now, the heat produced is proportional to the amount of current square. Okay, so if current passes through the wire, the amount of heat produced is the square. Okay, so H is proportional to I square. Now, heat is also proportional to the resistance. Heat is also proportional to temperature. So in total, combining all this, I can say heat is proportional to I square RT. Can I say that? Okay. Okay. H is proportional to I square RT. So I can say that H is equal to I square RT into, I have to put a constant. I will put a constant K. Yes. H is equal to K I square RT. So K, let's say K is approximately equal to 1. If K is approximately equal to 1, then H is equal to I square RT. So this is Joule's law of heating. Okay. H is equal to I square RT. Now what does this say? This just says that you have a wire. If current passes through it for a long time, it will produce heating. And the amount of heat is given by I square RT. Simple concept. Okay? Yes. Vijay Kumar, I already told you, dear, I will take the class at 8 p.m. in the evening. Okay, you can go to college during the day and come back. Come back, have your dinner, relax and attend the class. Okay, all my classes will be at 8 p.m. Not every day, but whenever I take class, it will be at 8 p.m. Okay? Okay, Vijay? Okay. Now some applications of heating effect. What are the applications of heating effect? There are so many. Electrical bulbs, fuses. Okay, let's look at fuses. So what is fuse? If you have a wire, you connect it to another fuse and then the wire. Okay. So what happens is, let's say this wire allows some value of current I. Okay. Now the fuse, it melts. If the value of current is greater than I, the fuse melts. So here you have two different wires of two different melting points. The outer wire has a higher melting point and the fuse has a lower melting point. So even if high current comes, it can pass through the outer wire, but it cannot pass through the fuse because the fuse melts. Okay. So fuse will melt. So this is an application using heating effect. So heating effect is used as fuse here. So it can cut the current. So current will not pass. So for example, this fuse is big, before some appliance, it cuts the current to the appliance. So your appliance will be safe. Okay. And then, different things. Electric heaters, irons, toasters, bulbs, they all use heating effect. Okay, that's done. Now, I think we can move on to power. Let's look at power also. Where do I have that? Electric power. What is electric power? What is electric power, students? Electric power, mathematically, I can say that power is work done by time. Okay, so it is basically electric work. Electric work, the whole divided by time. So, how fast electrical energy can be converted into whatever useful form of energy? For example, in your light bulb, the moment you switch on, how fast the electricity is converted into light? It gives you the power. Okay, it tells you the rate at which work is done by a battery or by some source. Okay, in maintaining electric current through, sorry, students. Yeah. Okay. It tells you it tells you about the work done in maintaining a certain amount of electric current through a fan. Okay. So that's electric power. The definition also I've put it here. 1 second, students. I just got a call. Okay. Okay. Now what will the SI unit be? SI unit will be work is joules, time is seconds, so joules per seconds. The SI unit can also be called as watts or W. Okay, so I can say 1 watt. 1 watt is 1 joule divided by 1 second. Okay, yeah, okay. Now, from this, I can do some more calculations regarding power. So, I know power is equal to work done by time. Okay. So, I know power is equal to work done by time. From this, I can also say that work done is what? VQ divided by T. Yes. So, from this, what is Q by T? V into I. So, now I have a new formula. Power is equal to voltage into current. Okay. So for doing these kinds of things, you need to know your previous chapters as well. Okay. So every chapter is important in second PU, especially for those of you who are preparing for KCET, JEE, NEET, and all that. Okay. Yeah. So this is one formula. Now I can write down other formulas also. I also know that power is equal to what is voltage. Instead of voltage, I can write it as current into resistance into current. So this is basically I square R. Okay. Now, instead of current, I can write it as voltage by resistance. So this will be V square by. Do you understand this part? Okay. So what did I do? In the formula VI, first I substituted V, then I substituted I. So I get two equations. So these are all different formulas for electric power. Okay. Yes. Is this clear to all of you? Super. Doing well. How are you? Tired? Happy? Excited? Let me know in the comments how the class is so far. Okay. So now you have 3 formulas for power. 4 formulas actually. Power is work done by time. Voltage into current. I square R. V square by R. Okay. Okay. Now let's look at the commercial unit of electrical energy. Okay. The commercial unit of electrical energy, like in your households and all that. What is a commercial unit? So you should know that. This is general knowledge, not just for your board exam, but for general knowledge. I want all my students to be smart students. Okay. So if somebody asks you how do you measure electricity at your house, you should say kilowatts per hour. Okay. So you should know that. After studying full chapter of electricity, if you don't know that, that's not nice. Okay. So you should know that. So what would that be? You can say, so 1 kilowatt hour is basically 1000 watts into hour to seconds is what? 3600 seconds. So this is basically 3.6 into 10 raised to 6 joules. Okay? Okay? Okay. Now let's look at another rule, which is the proof of Joule's law of heating. So I am going to prove that H is equal to I square RT. Okay. How do I prove that? How do I prove H is equal to I square RT? H is equal to I square RT. So what? I will take the formula for power first. So what is power? Power is equal to I square R. Okay. Now also we know that power is what? The amount of energy divided by the amount of time. Yeah. So now I can equate the two. So energy by time is going to be equal to I square R. Okay. So energy time is by time is going to be equal to I square R. So from this, energy is equal to I square RT, the whole divided by, energy is equal to I square RT. So energy is the same as the amount of heating, which is I square RT. Very easy derivation. So this is a proof for Joule's law of heating. Okay. Is this clear? 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 Yes? No? Okay. Students, from now, after this, most important topic, Kirchhoff's laws. Okay. Now, where we have little more portion only, Kirchhoff's laws, Wheatstone's bridge, cells in series, cells in parallel. And then we are done with chapter current electricity. One shot in 2 hours, I'll try to finish. Maximum 2 hours, 15 minutes, not more than that. Okay. Now, imagine, if I don't finish at that time, please don't look at the YouTube time and comment, okay? Okay. Yeah. I was just, giving a voice rest to myself. Since it's a one shot, I don't want to take a break in between. So there are so many, Kirchhoff gave out so many laws. First, we look at the first law. First law is also called as the junction rule. Okay. So imagine you have a junction and you have some currents coming in and out. Okay. So if you have a current I1 coming in, I2, another current I2 coming in, let's say I3 is going out. Okay. I4 is also going out. I5 is also going out. Okay. So there's a junction. Some currents are coming in, some currents are going out. Now, if you take the currents coming in, which is I1 plus I2, it will be the same as the currents going out, which is I3 plus I4 plus I5. Okay. So the amount of current coming in is equal to the amount of current going out. That is Kirchhoff's junction rule. What does it also mean? The algebraic sum of currents entering a junction is equal to the sum of currents leaving the junction. Okay. So all the currents entering the junction will leave the junction. Okay. So the amount of current entering the junction is equal to the amount of current leaving the junction. Now this is based on the conservation of charge. Very important, students. You might get a 1 marker or a fill in the blanks, choose the correct option to ask. They might ask you, what is Kirchhoff's first law based on? So it's based on the conservation of charge. So here charge is conserved, right? There is no charge gained, there is no charge lost. Whatever charge comes in, that much charge goes out. Okay? It's easy, no? Kirchhoff's first law is easy. Now let's come to the second law. Second law is something that's tricky to some of you. Some of you it's very easy. Okay? So Kirchhoff's second law is also called as Kirchhoff's voltage law. Some people also call it Kirchhoff's loop law. Okay. So this law actually states that the algebraic sum of the potential difference in any closed loop is 0. Okay. So according to Kirchhoff's second law, the algebraic sum of potential difference around a closed loop is 0. It is based on the conservation of energy. It's based on the conservation of energy, and this is the definition. The algebraic sum of all potential differences is 0. Now, before we look at, I will show you Kirchhoff's voltage law with a diagram and an example like I showed you first law. Let's look at, some sign conventions first. Sign convention, very important. If you know sign convention thoroughly, students, Kirchhoff's voltage law is going to be very easy for you. Okay. So first thing, if you have a resistor, okay, of resistance R, and let's say current I, okay, let's say current I, okay, there is a resistance which has a current I passing through it. Now, if you are measuring things, okay, let's take two resistances. Okay, so there's current I. Now, if you are taking measurements in the direction of current, okay, then you will take it as plus IR. Now, if you are taking measurements in the direction opposite to the direction of current, then you will take minus IR. Is this clear to all of you? This is very important. Okay. So if you have a resistor and you have current passing through it, if you're taking measurements in the direction, it's plus IR. In the opposite direction, it is minus IR. Okay. Now, one more thing that you need to know. If you have a cell, okay, you have a cell, this is positive, this is negative, you know that. You have, let's say you have, okay, if you have a cell, okay, and let's say the EMF of the cell is E. Alright, let's the EMF of the cell be E. Now, if you're taking measurements from the positive terminal to the negative, you take it as minus E. If it is from the negative to the positive, you take it as plus E. Okay, students, if you know these four things, if you know these things, then this Kirchhoff's voltage law is going to be very easy for you. Okay, so quickly take a screenshot of this and then we will do questions based on this. I will apply this in an example and show you too. It will be a little more clear to you. Okay, so if you have current and resistance and you have plus IR, you're measuring it in the direction of current, it's plus IR, opposite direction of current, minus IR. If you have a battery or a cell, if you're taking measurements from negative to positive, it's positive. Positive to negative, it's negative. Okay? Yeah. Let's do a question based on Kirchhoff's voltage law. Okay, let's consider a simple circuit. Okay, let me take a simple circuit. So let's put a resistor, okay, a battery. I'll put two batteries and two resistors. So you properly understand what's going to happen. Okay, I have a circuit which has two batteries and two resistors. Okay, so I will erase this part. It's too much color. Yeah. Okay. Now, if this is E2, this is E1, okay? So first battery I will name it as E1, second battery I will name it as E2, okay? Now, from E2, there is a current, okay, this is a series circuit. So everywhere current will be what? I. Series circuit, no. So current is going to be I. Now resistance, let me put it as R1 and R2. Okay. Now, you can either evaluate this clockwise or anti-clockwise. It's not going to be a matter. Okay. That is your decision. So now I will do it clockwise. Okay. So I will do it clockwise. Clockwise means like this. So I will start from this point. Okay. I start from this point. So first, what do I have? I have I1 R1. Okay. I1 R1. So should it be positive or negative? Obviously, it should be positive. Why? Because I am measuring it along the direction of current. Plus, I2 R2 is also along the direction of current. I2 R2. Now, this should be equal to the EMFs. Okay. So, I'm coming this way. So, right now, for E1, I'm measuring from positive to negative. Positive to negative should be minus E1. Plus, when I reach E2, I'm going from negative to positive. So, it's going to be plus E2. That's all, students. Very easy, no? Yes. Is this easy for you? Now, if you're attending live classes, if you have doubts, you can ask me. But if you're attending a recorded class, then it won't be possible. Sanat, yes. Battery negative to positive. Yes. Yes, yes. So what did I do here? I will just represent it once again on the marker. Okay. Now I'll take this. Okay. So I started from here. Okay. So first I go this path. I go along this path. So what is this? I1, R1. It's along the direction of current. So it's positive. Then I go here. So I2, R2. I R2. It's all again along the direction of current. So it's positive. Now when I reach here, you can see that I am going from positive terminal to negative terminal. That's why I took minus E1. Okay. And then when I reach here, it's from negative to positive. So this becomes plus E2. Okay, that's all. Now we'll do a little more advanced question, one more question, so that you understand a little more better. Okay, so let's take a little more complex circuit. Let's put one resistor. I'll put another resistor, another resistor. Let me put a cell here, another resistor. Okay. I can put one more resistor here. I'll put another cell here, another resistor here, and then I'll close. So this is my circuit. Okay. Samat, I see your message. Can you tell me what your doubt is? I just saw battery negative to positive, and then ma'am. So what is your doubt? Okay. So this is my figure. So let me name the resistors. I'll start from here. So this is R1, this is R2, then this will be R3, this will be R4. So I'll put this as R5 and I'll put this as R6. Okay, are you all happy with this? Yeah, and this I'll put it as E1, this I will put it as E2. Okay. Now, this is a parallel circuit, two series together forming a parallel. So, obviously, current is not going to be the same. Okay. Now, from this battery, if current I1 comes out, and from this battery, let's say current I2 comes out. Okay. Okay, let me put this as 2 and this as 1. So, it's better. So let this battery have I1 coming out, this battery has I2 coming out. When it reaches this point, what comes out here? Here it will be I3. I1 and I2 together, it will be I3 coming out. Okay? Previous diagram E2 should be reverse. Previous diagram E2 should be reverse. Why E2 should be reverse? Positive. I don't understand. Previous diagram. Why should E2 be reverse? Minus plus. Okay, let him come back with his doubt and then we'll clear that. Okay, so I1, I2 together you get I3. Can you explain why, Sanath? I didn't get your doubt. So here also I3 passes. Okay, here also I3 passes. But here what happens? Here on this arm it's I2. Okay, this arm also it's I1. Why I1 and I2? Because that is part of one circuit. So same wire. So same wire is I1, the rest same wire is I2. Okay? This is the figure. So first thing I can write from this is I1 plus I2 is I3. Yes, I1 plus I2 is I3. Okay? Oh, like that, Sanand. Okay, that was just a question where I, showed you how to take it out as Kirchhoff's law. Okay. Okay. You don't have to look at it that way. Okay. Ideally, you don't have to look at it. That was just a circuit where I put all the components and I put the batteries in two different ways. So you understand how to take it in two different ways. Okay. So in that circuit, the only aim of that circuit was for you to understand how to write a KVL. The line from that. So only if I put battery in opposite way, then you'll understand how when to take minus E and when to take plus E. Okay. For only that I did that. Okay. Yeah. Good. I like your observation. So I1 plus I2 is I3. So you can see from cell I1, I2 comes, they combine together, go as I3. Now let's name the loop. Okay. Let's call it loop ABCD. So let this point be A, B, C, D, E and F. Okay. Okay. So in loop A, B, C, D, A. Okay. Loop A, B, C, D, A. Let me write down the formulas. Let me use red. So what happens first? Let me start from this side. Let me start from I3, R3. Okay. So from where am I starting? I'm starting from this side. Okay. So I start from there. So I have I3, R3. So I3, R3 plus. What is the next one? I have I3, R1 plus. Then I have I3, R2. And then where does it come? Okay, let me draw it along with here. So first I3R3 and then I3R1, I3R2 and then I come down, I reach here. So this is what? This is I2R4 and then I reach the cell. That's the path. Okay. So plus I have I2R4 and then I reach the cell. So will it be positive E1 or negative E1? Tell me. Yes, it will be positive E1 because I'm starting from negative going to the positive of the battery. From negative of the battery to positive of the battery. So it will be positive E1. Okay. Now in loop, what do I call the loop? So I'll start from F. So I'll call it FADEF. Okay. In loop FADEF, how will it be? It will be, I start from point F. So what is the first one? I1 R5. And then it goes to, so the cell I will ignore it. I will write it at the end. Okay, I'll put only the resistors first. Then I'll go to R2. Sorry, I2. I2 is negative. Minus R4 I2 plus I1 R6 is equal to the two cells. So the first cell is from positive, so it's minus E1 plus. The second cell is plus E2. Now for those of you who still haven't understood, I will explain it once again. Students, I have started from, let me take a different color. Blue. Okay. So I started from this point. Okay. So from here I go. What is my first resistance? It's R5. Through R5, what current passes? I1 current passes and it's along the same path, so it's positive. So this is how I get I1 R5. And then I go to this path. There is a battery. Let's wait for the battery. And then I reach here. What is here? I have I2 R4, but current flows along I2 R4 in which direction? In this direction. So the direction of current flow and the direction in which I have come is opposite. So minus I2 R4. And then what happens? It comes down to I1 R6. I1 R6 is positive because it flows in the same direction. I measure in the same direction. And then I reach E2. So in E2, how do I go? I go from negative to positive. So whenever I go from negative to positive, it's positive. So my above cell, went from positive to negative. So it should be minus E1. So that's how I have minus E1 plus E2. Is this clear to all of you? Yes. So if this is not clear to all of you, I want you to pause this video, go back, reduce the speed, watch it once again. I am sure it will be clear to you. Okay? Okay. Now let's look at almost the last point. I mean, not the last topic, but yeah, almost. Is Wheatstone's bridge. So Wheatstone's bridge is basically a simple bridge. It helps you measure unknown resistance. Okay, so it is used in meter bridge, potentiometer, and all, but all that is removed from your syllabus. But in your practicals, you might have done meter bridge. Okay, so it is basically a bridge that helps you find out unknown resistance. All right. Okay. Okay. Yeah. So it works on the principle of null deflection. I will explain all that to you. So let's start Wheatstone's bridge. Are you all ready to do Wheatstone's bridge? Okay. Oh my god, Akshay has put a big message. Physics becomes much easier to understand through YouTube classes. Through your YouTube classes. Okay. The way you teach, explain clarity, real life example, diagram. Okay. Thank you so much, Akshay. Yeah. It means a lot. Okay. So please mention that in the comments as well. So, when a random person comes, takes the video and checks the comment and sees these comments, he'll be more motivated to watch the video. That's one help you can do for me. Thank you, Akshay. Okay, let's draw a meter bridge setup first. I mean, a Wheatstone's bridge setup first. So what I will do is, I will draw 4 resistances. Okay, I will draw 4 resistances like this. Okay, and I will connect it to a battery. A battery and a cell. Okay, so this is my basic Wheatstone's bridge setup. So what all do I have? I have 4 resistances. Okay, I will name them P, Q, R and S. Okay, the 4 resistances I will name them P, Q, R and S. Now through the center, I will connect a galvanometer. Okay, I will connect a galvanometer through the center. Okay. So what is galvanometer? Galvanometer is a device that will detect very small currents. Okay, so if there is current, it will deflect. If there is no current, it will not deflect. That's all. Simple. Okay. Now let me do. I will do Kirchhoff's law itself here. So, but yeah, I will show it. So first thing. So this is V. Okay. From V, you have a current I. Let's take a different color. You have a current I, let me take which color? Orange. Okay, current I. So once it reaches this point, this splits into I1 and I2. Okay. So current I splits into I1 and I2. Now what happens? Through the galvanometer, there is a current Ig. So what passes through R, resistance R? So through resistance R, the remaining goes I1 minus Ig goes. Okay. I1 goes through P, Ig goes through galvanometer. So through R, I1 minus Ig goes. Okay. Now this is the direction. Okay. So now I2 and Ig, they both come together and they go to Is. So in S, what will the value be? It will be I2 plus Ig. Okay. And then current I comes back. Okay. I know I should have drawn a better picture. Thank you so much, Akshay. I've seen your message. Thank you very much. Okay. So S will be I2 plus Ig. Do you understand this? Is the diagram clear to all of you? Okay. Now let's draw the loop. So where will I put the loop? So I will put this as A, B, C and D. Okay. A, B, C and D. Alright. So in loop A, B, B, A, which is the first part, which is this much. Okay, in this much, let's see what happens. So first, I1P. Okay, I'm starting from point A. From point A, there's I1P. And then when I come down, again, I1G, I1G. But when I go to this arm, when I go to the third arm, it's like a triangle, right? When I go to this arm, then it's negative. See, I2 is in the opposite direction. So this becomes minus I2Q. The whole thing should be 0. Okay. So what I'm deriving here, okay, I forgot to mention that this is basically, what I'm deriving here is balancing condition. Okay. The balancing condition. I think I have a slide. I should put it there. Okay. Yeah, I have a slide here. Okay. Same thing. What I do here is a balancing condition of a Wheatstone's bridge. Okay. So I have the first formula I1P plus I1G minus I2Q should be equal to 0 because when the Wheatstone's bridge is balanced, it should be 0. Okay. Alright. So I1P plus, see, galvanometer shows no deflection during balancing condition. So current should be 0. So 0 into G minus I2Q should be equal to 0. So this gives you I1P is equal to I2Q. This is my equation 1. Okay. Now I will take the next equation. I will write that on the next page. So what I will do is I will copy this. I will copy this down. Okay. I think I removed it, no? Yeah. I wanted to copy it, but it's okay. Okay. So now what I should take the other loop. So in loop B, C, D, B. Okay. In loop B, C, D, B, what happens? I1 minus Ig. So my starting point is point B. Okay, my starting point is point B. So from point B to C, what is it? I1 minus Ig into resistance R minus. Okay, that is positive. Minus. From C to D. From C to D, current is in this direction. Current is in the direction opposite to the direction I am coming. So it will be S is the resistance. S into minus S into I2 plus Ig. Then it goes up minus Ig into G. This whole thing should also be 0 because it's for balancing condition. So for balancing condition everywhere Ig should be 0. So this becomes I1R minus IGS is equal to 0. Why? Since Ig is equal to 0, balancing condition. Okay. So from this what I get is I1R is equal to I2, sorry. This is not Ig. This is I2. Yeah. I1R is equal to I2S. Okay. Now if I take both my equations, this is my equation 2. If I divide equation 1 by equation 2, what do I get? My equation 1 was I1P is equal to I2Q, the whole divided by I1R is equal to I2S. Okay. Now when you cancel I1, I2, you will get P by R is equal to Q by S. This is the same as P by Q is equal to R by S, which is the balancing condition for the Wheatstone's bridge. Okay, so P by Q. So if you have the resistances, okay, so the resistance, this resistance divided by this resistance should be equal to this resistance divided by this. P, Q, R, S. So P by Q should be equal to R by S. Okay. So students, for balancing condition, you need to do this part as well as this part. Okay. Yes. So this also, if you understand, it's very easy. Okay. But you need to understand. Alright. Yes. Okay. Next, what we're going to look at is relationship between EMF and internal resistance. And then one more topic, we are done. So what is the relationship between EMF and internal resistance? Okay. So some key important topics you need to know here, definitions which you already know by now is what is EMF, what is terminal voltage, what is internal resistance, what is current, what is external resistance. All this you already know. What is EMF? It is the potential by a cell when there is no current flowing. Okay. So if this is a cell and I just connect a wire, nothing else, then the potential, the total potential of the cell is the EMF. Terminal voltage is the terminal across the voltage across the terminals of the cell when current is flowing through it. Okay. And what is internal resistance? The resistance offered by the internal components of the cell. Current and resistance, you already know what it is. So to derive the relationship between EMF and internal resistance, let's first have a circuit. Okay. So first thing, let's have a circuit. Now we are going to consider a case where discharging happens. Okay. So when discharging happens, let's say my circuit is, I put the circuit here. You have a resistor, you have a cell. Okay, that's enough. Basic circuit. So resistor has a value of R. EMF of the cell is E. Internal resistance of the cell is R. It's a series cell, so it will have a current of I passing through it. So let's use Kirchhoff's law itself. So initially there is IR plus. When you go through the cell is also from negative to positive. So it's plus E, no, not E, plus same current passes through the cell. And the cell also has a resistance. So it is basically I into small r should be equal to E. Do you understand that? This is when discharging happens. So IR1, so what did I do? Which path did I take? From here. Okay. IR1 plus IR small r is equal to E. Okay. So now from this I can say that E is equal to I, if I take outside, it's basically R plus R. Yes. Okay. Can I say that? Okay. I can say that. I can also say this IR, I can also say it's V. So this I can write it as V plus IR is equal to E. Can I do that? Now from this I can also say that V is equal to E minus IR. Yes. So this is the relationship between EMF and internal resistance. Yes. Okay. Now if I compare it with the equation, y is equal to mx plus c. So this will be y is equal to c plus mx. Okay. So let's say, let me try to draw a graph. If I have v and I, what is my y-intercept? My y-intercept is E. So obviously if this is a graph, this should be E. Now my slope is going to be minus R. That is why I have drawn a downward graph. This is minus R. Okay? Yes? Okay? Is that clear to all of you? So my slope is going to be minus R. If I compare v is equal to E minus IR, if I compare it to y is equal to mx plus c. So my intercept, what is y-intercept? The line where the graph touches the y-axis. So that value should be E, and the downward slope, so it's minus R. Okay? Yeah. So slope is basically minus R. One small thing that I made a mistake here, not made a mistake, this is basically small r. isn't it? Small r. So here also slope is smaller. Yeah, big R got converted into V. Yes. Now, if it's discharging, okay. So if it's discharging, that's not important, but yeah, I'll just tell you. Sorry, if it's charging, okay. So when something is charging, then the formula will be V is equal to E minus IR. So this will be equal to E plus IR. Okay. Now why this happens? This happens because you change the direction of current. So when something is charging, current flows from this side. So what happens? The whole thing, sign changes, that's all. When it's discharging, current flows along the direction in which I have mentioned. If it's charging, it flows in the opposite direction. So it becomes E plus IR. Is that clear? Okay. Now last two topics that we're going to finish today's class is with cells in series and cells in parallel. So we already looked at resistors in series and resistors in parallel. So now we look at cells in series and cells in parallel. So what do you mean by cells in series? Cells in series just means that you have some cells, okay? You have some cells, okay? And each of them has an EMF E1, E2, E3, and they have internal resistance R1, R2, R3, okay? But they have the same amount of current passing because they are in series, okay? Same amount of current. So if so many cells are in series, if positive is connected to the negative to positive, like that alternate way, if it is connected, it is in series, okay? So we already saw total resistance in series is what? R is equal to R1 plus R2 plus R3. Already learned? Yeah. Now total EMF will be what? EMF will be E1 plus E2 plus E3, depending on how many are there. E1 plus E2 plus E3. E1 plus E2 plus E3. Now total potential will be what? V will be equal to V1 plus V2 plus V3. This thing I've already taught you so many times. In series circuits, only current is same, voltage is different. Now we know the formula. What is the formula? E minus IR is equal to E1 minus IR1 plus E2 minus IR2 plus E3 minus IR3. Okay. So I'll take all the E terms outside. So I'll get E minus IR is equal to E1 plus E2 plus E3 minus I'll take outside R1 plus R2 plus R3. Now this I can write, if I want, I can write it as E minus IR is equal to E effective minus IR effective. I can write it like that as well, but not required. Okay. So this is the formula for total so many cells in series. Okay. So I will put n here if there are n cells. N. Okay. Now same thing if I do in parallel, I'm done with today's class. Last and final topic, same thing I'll do in parallel. So what should the difference be? Instead of R is equal to R1 plus R2 plus R3, total resistance in parallel is 1 by R is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Okay? That's the only difference. So let's do that. So cells in parallel. So this is one. So this will be one cell. This will be another cell. This will be another cell. Okay. So current. So from this cell, let's say a current of I1 comes. Okay. From this cell, a current of I2 comes. From this cell, a current of I3 comes. Together, they go out as current I. Okay. Because it's series, parallel. Current is different. Okay. So this is E1, E2, E3. This will have R1, R2, R3. And they will all have the same voltage. So let's write on the first formula. Formula for total resistance is 1 by R1 plus 1 by R2 plus 1 by R3. Now what will the EMF be? So EMF will be EMF divided by Rn divided by E1 by R1 plus E2 by R2 plus E3 by R3. Now we also know that current is equal to I1 plus I2 plus I3 because this is a parallel circuit. So what does this become? En minus V by Rn is equal to E1 minus V by R1 plus E2 minus V by R2 plus E3 minus V by R3. This is the formula for cells in parallel. Okay? Is this clear to all of you? Yes. With this, we are done with one shot current electricity. I think I took like 5 minutes extra. Yes? Is this clear to all of you? Any doubts? Any doubts? Anything that you want to answer? Sorry, my phone just dropped. Any doubts? Anything? Okay, good. Good. Very good. Very good. Very good. Okay. So this is a gist of current electricity in a one short video. So in the next class, I will be doing questions on this class. Okay. The next class will be maybe recorded. So please go to Vedantu Karnataka channel and check for recordings. So it could be a recorded class, might not be for sure a live class. Okay. So I hope this is clear all of you. Yes. Okay. So with that, we come to an end with today's session. I'll see you all with another rocking banging section in the next class. So please let me know in the comments on how the class was. Okay, I'm very excited to know that, students. See, when we're only talking to a screen here. Okay, so all of these YouTube teachers were very curious to know on what's happening on the other side. So only if you let us know in the comments, we know how we're doing. Okay, so please let us know in the comments. I would love to hear your comments. Okay, bye bye.